The concepts of Hamiltonian and Lagrangian offer powerful frameworks for understanding and analyzing the dynamics of physical systems. In classical mechanics and mathematical physics, developed by Lagrange and Hamilton, these formulations provide alternative perspectives that complement each other. The Lagrangian formulation, introduced by Lagrange, describe mechanics based on the principle of this action. The Lagrangian, the difference between kinetic and potential energy, captures the system's dynamics and depends on generalized coordinates and velocities. The Euler-Lagrange equations are derived by varying the action integral describing the system motions. In contrast, Hamilton's formulation provides an alternative approach using generalized coordinates and momenta. The Hamilton obtained from the Legendre transform of the Lagrangian represents the system's total energy. Hamilton's equations describe the time evolution of coordinates and momenta. Together, the Hamiltonian and Lagrangian formulations offer comprehensive insight into system dynamics. The Lagrangian emphasizes the principle of this action, while the Hamiltonian focuses on symmetries, energy, and coordinate momentum evolution.
Example of Hamilton's variational principle. Hamilton's variational principle is a foundational theoretical physics concept with far-reaching implications and applications across a wide range of disciplines. This discipline allows us to determine the most efficient and optimal physical system paths, trajectories, and behaviors by minimizing the action integral. From the behavior of light in optics, the motion of particles in mechanics, and the wave-particle duality in quantum mechanics to behavior charge in electromagnetic field, the flow of fluids in fluid dynamics, and the dynamics of fields in field theories. Hamilton's variational principle provides us valuable insight and equations that help us understand and predict the life phenomena. In, in fields like fluid dynamics and aerospace engineering, this principle enables engineers to optimize design and trajectories, minimizing cost and maximizing efficiency. Overall, Hamilton's variational principle is a fundamental and versatile tool that analyzes many fundamental concepts and calculations in physics. The example of generalized coordinates. Lagrangian mechanics provide a powerful framework for describing the dynamics of systems using generalized coordinates. By introducing these coordinates, which represent the important variable of a system, we can derive the Lagrangian function that captures the essential physics of the system. This approach offers a more elegant and concise way to analyze the dynamics compared to the traditional Newtonian mechanics. The Lagrangian difference between system kinetic and potential energy allows us to obtain the equation of motion that govern the system behavior. This framework finds application in various real-life scenarios, such as the motion of pendulums, particles, moving particles, constant motion, and rotation of rigid bodies. By utilizing appropriate generalized coordinates, Lagrangian mechanics enable us to effectively describe and analyze the dynamics of complex systems.
In Hamiltonian and Lagrangian mechanics, the calculation of kinetic and potential energies is an essential step in describing the dynamic of a system. Firstly, simple harmonic oscillator. Consider a mass spring system where a mass is attached to a spring and oscillates back and forth. In Lagrangian mechanics, the potential energy of the system is given by the elastic potential energy stored in the spring, which is proportional to the square of the displacement of the mass from its equilibrium position. The kinetic energy is calculated based on the mass velocity. By combining these energies, the equations of motion can be derived. Secondly, planetary motion. In celestial mechanics, the motion of planets and satellites around a central body can be described using Hamiltonian or Lagrangian mechanics. The potential energy in this case is the gravitational potential energy between celestial bodies, which depends on their masses and the distance between them. The kinetic energy is calculated based on the velocities of the objects. By considering these energies, the equations of motion for the system can be derived. Thirdly, double pendulum. A double pendulum consists of two pendulums connected to each other, creating a complex system with rich dynamics. The potential energy is calculated based on the height of each mass above a reference point, while the kinetic energy is determined by the mass's velocities. The Lagrangian or Hamiltonian can be derived. Can be formulated using these energies, allowing for the derivation of equations that describe the motion of the double pendulum. Fourthly, quantum systems. In quantum mechanics, both Lagrangian and Hamiltonian formalisms are used to describe the dynamics of quantum systems. For example, in a quantum harmonic oscillator, the potential energy arises from the spring potential, while the kinetic energy is related to the momentum of the quantum particle. These energies are used to construct the Hamiltonian operator, which governs the system's evolution in time. Lastly, field theory. In classical field theory, such as electromagnetism, Lagrangian and Hamiltonian frameworks are used to describe the behavior of fields and their interactions. The potential energy is typically associated with the interaction between the field, while the kinetic energy corresponds to the field derivatives. By considering this equation, the equation of motion of the system can be derived. In simple harmonic oscillator, consider mass m attached to a spring with spring constant k. The system has a single generalized coordinate, which is the displacement x of the mass from its equilibrium position. The potential energy is given by V is equal to half kx squared, and the Lagrangian is L is equal to T minus V, where T is the kinetic energy. Applying Lagrange's equation, we obtain d over dt partial derivative L over partial derivative dx over dt minus partial derivative L over partial derivative x is equal and d square x over dt square plus kx is equal to 0. Secondly, gravitational system. Consider a particle of mass m moving in a conservative gravitational field near the Earth's surface. The generalized coordinate is the vertical displacement y of the particle. The potential energy is given by V is equal to mgy, where g is the acceleration due to gravity. Lagrangian is L is equal to T minus V, and applying Lagrange's equation yields d over dt partial derivative L over partial derivative dy over dt minus partial derivative L over partial derivative y is equal to m d square y over dt square plus mg is equal to 0. Thirdly, pendulum. Consider a simple pendulum consisting of a mass attached to a fixed point by a massless rod of length L. The generalized coordinate is the angular displacement theta of the pendulum from the vertical position. The potential energy V is equal to negative mgl cos theta, where g is the acceleration due to gravity. Lagrangian L is equal to T minus V, and applying Lagrange's equations yields d over dt partial derivative L over partial derivative d theta over dt minus partial derivative L over partial derivative theta is equal to ml square d square theta over dt square plus mgl sin theta is equal to 0.
Next is application of Lagrange's equation. There is some application including harmonic oscillator, center force field, atom emission, double atom emission, raging body, and particles sliding on a movable equilibrium plane. For harmonic oscillator, the Lagrangian equation is shown above, and after we carry out the Lagrangian operation of equation, we can obtain the equation motion of the Adam harmonic oscillator.
Then we can apply the Lagrangian equation for single particle in central force field. First, we need to generalize coordinate. Then we can obtain the Lagrangian equation. We can also obtain the square of the particle velocity by expressing the velocity vector in terms of radial and tangential unit vector. We need to implement the Lagrangian equation, and there will be an equation of motion for single particle in central force field. Next is we have exhaust machine and double exhaust machine. For exhaust machine, there is two weight of mass. In this figure, the weight connected by an ideal mass in an extensible string of length and moment of inertia. And for the double exhaust machine, we have replaced of the weight in simple exhaust machine by second simple exhaust machine. The implication of this constraint regarding the reduction to the two selected generalized coordinate x and x prime. After write down the kinetic and potential energy for both system and generalized coordinate of the system, the final acceleration for a two machine was obtained. If one m1 bigger than m2, m1 falls with constant acceleration and m2 rise with same acceleration, and if m1 equals to m2, they are remain at rest. For double atomic machine, the equation of motion can be obtained from an algebraic solution of the preceding equation. For Euler equation, for free rotation rigid body, consider the rotation is torque free and no potential energy, so the Lagrangian equation that we obtain is shown above. We can find the equation of motion by referring to the Eulerian angles as generalized coordinates. After several processes using chain rules, we will obtain equation which I1 omega 1 omega 2 minus I2 omega 2 omega 1, and the equation of motion in the coordinate will reduce to this equation. In Lagrangian mechanics, generalized momenta are quantities that are derived from a Lagrangian function and describe the conjugate momentum associated with the generalized coordinate of a system. Ignorable coordinates, on the other hand, are coordinates that do not appear explicitly in the Lagrangian function. If we have a Lagrangian function L, Q, Y, T, the Q represents the generalized coordinate and Y represents the time derivative of the coordinate. If a coordinate qk is ignorable, it means that it does not appear explicitly in the Lagrangian function L. Therefore, the associated generalized momentum pk is conserved. This implies that the partial derivative of the Lagrangian with respect to the corresponding coordinate derivative is zero. This ignorable coordinate simplifies the equation of motion and often lead to conserved quantity of symmetries in the system.
Find this in Hamilton's Virginia principle. In optics, Hamilton's Virginia principle is used to derive important equations such as Snell's law and Fermat's principle of last time. Snell's law describes the bending of light at interface between two media and different effective indices, while Fermat's principle states that the light takes the path that requires that the least time to travel between 2 points. In classical mechanics, Hamilton's Virginia principle provides an alternative approach to Newton's laws of motion. By minimizing the action integral, one can derive the equation of motion for mechanical systems such as the differential equation of motion for a simple pendulum. This principle is widely used to study dynamic and motion in various engineering applications. In quantum mechanics, Hamilton's Virginia principle is used to derive the Schrödinger equation, which describes the behavior of quantum particles in terms of their wave function. This equation is fundamental in understanding the energy levels and waves function of quantum systems, such as atoms and molecules. In electromagnetism, Hamilton's Virginia principle is applied to derive the equation of motion for charged particles in electromagnetic fields, known as the Lorentz force equation. It is also to describe the behavior of electromagnetic waves and derive the wave equation that governs the propagation. In fluid dynamics, Hamilton's rational principle is used to derive the equation governing the motion of fluids, such as the Euler equation for inviscid flows. This equation describes the conservation of mass, momentum, and energy in fluid systems. In field theories, such as electromagnetism and quantum field theory, Hamilton's rational principle allows for the derivation of equation of motion for field by minimizing the action integral associated with the field dynamics. This is crucial in understanding the behavior of fields and their interaction with other physical systems.
From what we can find in calculating kinetic and potential energies, the Lagrangian formulation offers a concise and powerful method for analyzing system dynamics. Expressing kinetic and potential energies in terms of generalized coordinates captures system behavior and enables the derivation of equation of motion. Kinetic energy is computed by considering the velocities associated with each generalized coordinates. Potential energy arises from force depending on the generalized coordinates and is expressed as a function of those coordinates. The Lagrangian is the difference between the kinetic and potential energies and is used to derive equations of motion. Real-life examples such as simple harmonic oscillator, planetary motion, double pendulum, quantum system, and field theory demonstrates the application of these concepts, provide a systematic approach to understanding and analyzing physical systems across various disciplines. What we can find in Lagrange's equation for motion for the conservative system. Lagrange equations of motion offers a powerful mathematical framework for analyzing conservative systems in the Lagrangian formulation. These equations derived from the principle of this action provide a concise and elegant way to describe how generalized coordinates and velocities evolve over time. Lagrange equations play a fundamental role in understanding and predicting the behavior of conservative systems, where potential energy depends only on the coordinates. The equations state that the time derivative of the Lagrangian's partial derivative with respect to velocity minus the partial derivatives with respect to the coordinates is zero. Lagrange equations allow us to determine the equations of motion for conservative system and describe the evolution of generalized coordinates. The framework is coordinate independent, allowing us to choose suitable generalized coordinates that simplify the problem or highlight system symmetries. Lagrange's equation provide a systematic approach to analyze systems with multiple degrees of freedom by considering each coordinate independently.
In Lagrangian mechanics, ignorable coordinates are those that do not appear explicitly in the Lagrangian function. As a result, they have no effect on the equation of motion and can be treated separately. The corresponding generalized momentum for this ignorable coordinate are constant of motion, remaining unchanged throughout the system motion. This is because the Lagrangian does not depend explicitly on the coordinate. Identifying ignorable coordinate and their associated constant of motion simplifies the analysis by reducing the number of equations to be solved. It allows for the separation of variables and reduce the problem's dimensionality, making it easier to find solution and gain insight into the system dynamic.
The discussion Hamilton's rational principle. In optics, Hamilton's rational principle is used to derive the equation of motion for light rays. By defining the Lagrangian as the difference between the kinetic and potential energies of the light ray, the action integral can be defined as the time integral of the Lagrangian. Applying Hamilton's rational principle allows us to derive the Econel equation, which relates the refractive index of the medium to the gradient of the phase of the wave function. This equation governs light propagation in media with varying refractive index and is widely used in lens design, fiber optics, and other areas of optics. In classical mechanics, Hamilton's variational principle is used to derive the equation of motion for particles and systems of particles by defining the Lagrangian as the difference between the kinetic and potential energies of the system and the action integral as the time integral of the Lagrangian. We can derive the Euler-Lagrange equation. This equation relates the generalized coordinates, their time derivative, and the force acting on the system. The Euler-Lagrange equations are second-order differential equations that govern the motion of particles and systems of particles, providing powerful tool for analyzing the dynamics of mechanical systems. In quantum mechanics, Hamilton's variational principle is used to derive the Schrödinger equation with describe the wave function of a quantum system by defining the Lagrangian as the difference between the kinetic and potential energies of the system and the action integral as the time integral of the Lagrangian. We can derive the Schrödinger equation. This equation relates the wave function, its time derivatives, and the system potential energy. The Schrödinger equation is a fundamental equation in quantum mechanics and is used to calculate the probabilities of different outcomes in quantum experiments. In electromagnetism, Hamilton's variational principle is used to derive the equation of motion for charged particles in electromagnetic fields by defining the Lagrangian as the difference between the kinetic and potential energy of the particle in the presence of electromagnetic fields and the action integral as the time integral of the Lagrangian. We can derive the Lorentz force equation. This equation describes the motion of charged particles in an electromagnetic field and is fundamental in understanding the behavior of charged particles in electric and magnetic fields. In fluid dynamics, Hamilton's variational principle is used to derive the equation of motion for fluid flow. In fluid dynamics, Hamilton's variational principle is used to derive the equation of motion for fluid flow by defining the Lagrangian as the difference between the kinetic and potential energy of the fluid and the action integral as the time integral of the Lagrangian. We can derive the Euler equation or the Navier-Stokes equation. This equation describes the motion of fluids and relates the fluid velocity, pressure, and the force acting on the fluid. The Euler or Navier-Stokes equations are fundamental in understanding phenomena such as the flow of fluids around objects, turbulence, and the behavior of fluids in various engineering applications. In field theories such as classical and quantum field theories, Hamilton variational is used to derive equations of motion for fields by defining the Lagrangian in terms of the fields, variables, and their derivatives, and the action integral as the time integral of the Lagrangian. We can derive the field equation that describe the behavior of the fields. This equation relates the field variables, their derivative, and the force potential acting on the fields. The field equations derived from Hamilton's variational principle in field theories are typically partial differential equations that cover the behavior of fields, and they are fundamental in understanding phenomena such as the behavior of electromagnetic fields, gravitational fields, and quantum fields.
The earlier statements provide an overview of how kinetic and potential energies are calculated within the Lagrangian mechanics, formulation, and their significance in analyzing the dynamics of physical systems. The Lagrangian formulation, based on the principle of least action, offers a powerful mathematical framework. It involves expressing the energies in terms of generalized coordinates, which provide a more flexible representation of the system's behavior. Kinetic energy determined by the velocities of the coordinates measure the system's motion. Potential energy arising from forces dependent on the coordinates represents stored energy. The Lagrangian, the difference between kinetic and potential energies, is crucial for deriving the equations of motion. For conservative systems, where potential energy only depends on the coordinates, Lagrangian equations are fundamental. These equations express the relationship between partial derivatives of the Lagrangian with respect to the velocities and coordinates, and they govern the system dynamics. By solving these equations, we can determine how generalized coordinates evolve with time and gain insights into the system's behavior.
Lagrangian equations are a versatile tool for analyzing complex systems with multiple degrees of freedom. They are simplified the derivation of equations of motion by utilizing generalized coordinates, providing a deeper understanding of system behavior. And the theorem connects Lagrangian equation to derivation of conservation law, such as angular momentum conservation from rotational symmetry. In quantum mechanics, the path integral formulation based on Lagrangian mechanics calculates transition amplitudes and probabilities by summing over all possible paths, contributing the quantum field theory and probabilistic interpretation. Lagrangian density describes field dynamics exemplified by deriving Maxwell equation for electromagnetism and applying Lagrangian formulation in the standard model of particle physics. In general relativity, Lagrangian technique formulate the field equation, allowing the student of gravitational phenomena. Lagrangian equations are also practical in engineering, enabling the analysis and control of mechanical systems, particularly in robotics. Overall, Lagrangian equations offer an essential and powerful framework in diverse scientific and engineering disciplines.
In conclusion, Hamiltonian's variational principle provides a powerful and elegant approach to understanding the dynamics of the physical systems. By expressing the system's behavior using generalized coordinates, the equations of motion can be derived, capturing the essential dynamics. Calculating kinetic and potential energies in terms of generalized coordinates offers a coordinate-independent framework, simplifying analysis and unifying the study of different systems. Lagrange equations of motion, derived from the principle of this action, provide a systematic and efficient for predicting and understanding the behavior of conservative systems with multiple degrees of freedom. Ignorable coordinates and generalized momenta offer further insight, with ignorable coordinates leading to conserved quantities and generalized momenta leading to facilitating the analysis of energies and dynamics. Together, these concepts form the foundation of classical mechanics, providing powerful mathematical tools to comprehend the fundamental principles governing the dynamics of physical systems.